Ok, entonces, bueno, voy a hablar en inglés porque nuestro invitado prefiere que hagamos esto en inglés. Em, Así que, bueno, hello everyone, thank you all for attending this seminar. Today the speaker is Pier Giovanni Bissiri from University of Bologna, who does research in the field of Bayesian statistics and non-parametric statistics, among others. So, Pier Giovanni, thanks for accepting our invitation. It is a pleasure having you here. So if you want, you can start.
Okay, thank you. Thank you for hello to everybody. Thank you for inviting me. I do research in actually in different areas, and one of them is geostatistics, where I studied the usage of Bayesian methods. So to begin with, I'll say a few words about the role of positive definite functions in geostatistics, and I'll focus about spheres, and I'll consider two major two particular conditions which you can consider. One is isotropy and the other one is axial symmetry. Then I'll introduce some Bayesian non-parametric models to model covariance on spheres. And about this topic, I'll refer in particular to a paper which I've published which is published in Bayesian analysis this year, and is a joint work with Emilio Porco, Felipe Tangle, Ruben Sosa, and Fernando Quintana. And at the end, I'll talk about the issue of strict positive definiteness. Matheron coined the term regionalized variable to designate a numerical function z of x depending on a continuous space index x. Geostatistics can then be defined as the application of probabilistic methods to regionalized variables. And generally, the main purpose is to estimate the value of a regionalized variable at places where it has not been measured. So from the mathematical point of view, the main object is a random field. So you consider a random field indexed at a subset of an Euclidean space, and the regionalized variable of interest is considered the realization of the process, and I'll focus about the case where the space where the random field is defined is the d-dimensional sphere. So the typical assumption is Gaussianity. This means that this is where you usually start, I would say. So you consider the process to be a centered stationary Gaussian random field. So basically this means that the finite dimension distributions of the process are Gaussian, and you have the expectation of every random variable z of x, which is 0, and in general we denote you have some function c, which is a covariance function. So in general, so this is a function that assigns to every 2 points x sub 1 and x sub 2 the covariance between z of x sub 1 and z of x sub 2. And so in this framework, the distribution of the random field z is characterized by the covariance function c. So the main purpose in general is kriging. Kriging means best linear unbiased prediction. Under the assumption the process z is a centered Gaussian random field, then the Kriging estimator coincides the condition expectation So we have the condition expectation of z of x naught, which is the point at which you want to predict the value of the process, given the values that we have observed of the process, which we denote by z of x sub 1, z of x sub n. And of course, this conditional expectation depends on the covariance function C. So, as I said, the main goal is the prediction of z at an unknown space or space-time location x naught, using variable information from the sample data, and we need the good estimation of the covariance function C to make a good prediction. So, as I said before, the distribution of the vector x sub 1, z of x sub 1, z of x sub n is normal with mean 0 and a covariance matrix which is capital sigma, which depends on the covariance function C, and this covariance matrix sigma is positive definite for every n-tupla of x sub 1, x sub n, if and only if the function C is positive definite. So, as I said before, we are going to consider the sphere as our as the space where we define the process, and this is related to the idea of apply the model to data, climate data, basically, or other data related to the Earth. So something which is known is that we need to consider, in this case, a distance, which the distance which you need to consider is the great circle distance. So if this is something well known, we can find in geostatistics books, and there is a lot of evidence telling us that if the study region is geographically extensive, distances computed between points on their surface should strictly be great circle distances. So the great circle distance is the length of the shortest path between 2 points on the surface of the sphere, moving along the surface of the sphere. The alternative would be the corner distance, which is the length of the path, of the shorter path, moving inside the sphere. So the right distance is the great circle or geodesic distance, which we denote by theta. Of course, in the application, we in practice, you consider a two-dimensional spheres. And okay, so from mathematically, the distances are cosine of the internal products of the 2 points x sub 1 and x sub 2. Okay, then as I said, we need C to so C is a appropriate covariance function if satisfies this property that I mentioned before, which is positive definiteness, which is due to the fact that we need this variance, of course, to be non-negative as a variance. And the mapping C that satisfies 1, this identity 1, or called as I said positive definite, if the equality is strict for any non-zero vector C sub 1, C sub n, then the mapping C is called strictly positive definite. Okay, then a condition which is which we may consider about the covariance is isotropy. So what does it mean that C is isotropic or geodesically isotropic? This means that basically the function C depends on x sub 1 and x sub 2 only through their geodesic distance, theta of x sub 1, x sub 2. So we have this identity when we have isotropy. So the C of x sub 1, x sub 2 depends on, is a product of sigma square, where sigma square is the variance of z of x, times psi of the geodesic distance between x1 and x sub 1 and x sub 2. So psi basically is, psi is a function which whose value 0 is 1, and basically it's a correlation. Here is a correlation function. And we denote by capital psi sub d the class of continuous functions psi, such that this identity is true and the function C is positive definite. So this is isotropy. We have introduced this space psi sub d, which depends on the dimension d of the sphere, and we have this property of inclusion. So each one of these spaces, so we have a sequence of spaces, and each space is a superset of the next space. And if you take the intersection of all these spaces, we get psi sub infinity. An important result is the Schoenberg theorem, which tells us that a function psi belongs to the space psi sub d if and only if it is a convex linear combination of normalized Gegenbauer polynomials. So the coefficients appear in this combination, linear combination, which we denote by B sub n d, form a probability mass sequence. So this means that they are non-negative and sum up to 1. In the cases where this is equal to 1, so the circle Gegenbauer polynomial simplified to Chebyshev polynomials, if this is equal to, which is the unit sphere of R3, they simplify to Legendre polynomial, and these coefficients are called the Schoenberg coefficients. So we have a similar result about psi sub infinity, where the normalized Gegenbauer polynomials are replaced by this simple function, which are cosine of theta raised to the n. So we have also we have this characterization about the function in psi sub infinity. And I just mentioned briefly these two papers. So there is the paper by Igniting, published in Bernoulli in 2013, provides all basic closed formulas about the relationships about this coefficient. So considering coefficients refer to one dimension and coefficient refers to another dimension. And basically, in the paper published in Sigma last year, which is a joint work with Di Melgato and Emilio Porcu, we find other relationships about these coefficients. But this is a technical paper, so I won't give you details about that. As I said, there is another condition about covariance function, which is axis symmetry, which is a less strong condition than isotropy. So here you are considering only two-dimensional spheres, and we consider a function C, which is a covariance function of the two-dimensional sphere. As this function is actually symmetric if depends on the 2 points x and x prime in this way. So it depends on the longitudes of the 2 points only through the difference of the 2 longitudes, whereas it depends freely on the latitudes. So this condition, so it's known that there is a characterization of all functions which satisfy positive definite function of the two-dimensional theory satisfy this condition. This characterization is given by Jones in his 1963 paper. And basically we have an expression where you have the associated adjunct polynomials, and basically the Schoenberg coefficients are replaced by this function, which I denote here by C sub m. So each one of these C sub m functions are positive definite functions as function from the space m plus 1, etc. times itself into the complex numbers. And we have a condition to ensure that the covariance function C is real valued. So this condition is written here is C of minus m is the complex conjugate of C of m valued in n and n prime. So this is basically a less strong condition than isotropy. We can recover isotropy if in particular the function C sub m, if the value C sub m of n and n prime is equal to 0 when n is different from n prime, is equal to some C of n if n is equal to n prime. So we have this condition about summability of these values, and basically in this particular case we recover isotropy, and you can obtain the Schoenberg sequence from the C of n sequence in this way here. So as I said, I'll talk about Bayesian parametric modeling, and so in this scenario we have we assume that our data are sampled from an isotropic Gaussian process with zero mean, and we aim at estimating the parameters of the model resulting to the Bayesian parametric approach. So using the Bayesian paradigm, this means that we are assigning a distribution to the parameters that we want to estimate, that we have in the model basically. And these parameters are sigma square and the sequence of the Schoenberg coefficients. So assigning a parameter, assigning a prior to sigma square is not difficult. Usually you choose a gamma distribution. It's not a difficult task. So it's more, of course, more complicated to assign a parameter, a distribution to an infinite-dimensional parameter, such as the sequence of the Schoenberg coefficients. So assigning prior to the sequence of the Schoenberg coefficients is the same as assigning a probability measure on the infinite-dimensional simplex. So which we denote by delta sub infinity, and which basically is the space of all real valued sequences which are non-negative and sum up to 1. So by Schoenberg theorem, this is equivalent to assess a prior probability measure on the space of correlation function, which we have denoted by psi, capital Psi sub d. So the deterministic sequence of the Schoenberg coefficient is replaced by random sequence, so a sequence of random variable, capital B sub n. So a sequence of random variables which are non-negative and sum up to 1 almost surely. So let's mention briefly how we can construct our model from the mathematical point of view. So we need to equip the space psi sub d with an appropriate topology, and the natural choice is to consider the topology induced by the unimor subnorm. And in this way, we can also consider a sigma field on the space of the correlation function, which we denote by tilde capital psi d, which is the corresponding Borel sigma field corresponding to the topology induced by the uniform norm. Instead, the simplex, the infinite dimensional simplex delta sub infinity is naturally equipped with the product topology, which is the smallest topology that makes projections continuous, and the corresponding Borel sigma field. So this is the mathematical settings of our model. We can consider a random correlation function, which is obtained simply considering convex linear combination of the normalized Eigenbauer polynomials, where the coefficients in this linear combination are the random variable b sub n. And we can prove that in the framework which I described in the previous slide, this object is a measurable map, and therefore is properly defined as random variable valued into the space of correlation functions psi sub d. Sorry, I'm going backwards for some reason. Okay, so how can we assign a proper probability measure, prior probability measure to our sequence of random variable b sub n? I want to be honest, there is not only one way of doing this. There are many ways, and one way is to resort to the stick breaking construction, which means that we consider a sequence of independent random variables valued into the unit interval. We denote them by w sub j. For some reasons that will be clear quite soon, we let the support of w sub j to be the full unit interval, and we have this construction here that we take b sub 0 equal to w sub 0, and you have this expression here, which is is a stick breaking. So basically means that it's difficult to explain. Maybe I should write something, but the idea is that it's like breaking a stick. The stick is the unit interval, so you break in a point which is given by w naught, and you get b sub naught. Then what is left is broken again according to w sub 1, and you get b sub 1. Well, I mean, let's say there is a reason why it's called stick breaking, and we have this condition here about the sum of the series, because you need to ensure that the sum of b sub n is equal to 1 almost surely. And I don't know why. Okay. And the relevant probability distribution for b is obtained through the stick breaking representation if, in particular, we consider the beta distribution, which is named the GM distribution, where you have this the W sub j being beta distributed with parameters depending on these two parameters, which are alpha between 0 and 1 and theta, which is greater than minus alpha. And this is a Griffith-Engen-McCloskey distribution, which is related to the Pitt-Mayor process. And in a particular case where alpha is equal to 0 is connected to the well-known Ferguson-Deschel process, which are models which are well-known in the Bayesian parametric literature. So the main thing we want to consider is the topological support of the prior distribution of our random correlation function. So let's recall what the support is. The support of our random correlation function is a set of all elements psi in the class psi sub d, such that the probability that our random correlation function belongs to any open ball centered at psi is positive. And so this is what the support is. Of course, support depends on the topology, which are considered, that in our case the uniform topology. We can prove that the fact that basically the support of W sub n is the whole unit interval. The other condition is, as I said, ensures that the sum of the log of the expectation of 1 minus W sub j equal to minus infinite is there to ensure that the sum of the B sub n is equal to 1. So this condition ensures that the support of our random correlation function is full. So is the whole space psi sub d in the subnorm. So basically we are saying that I can consider that the true correlation function which you want to estimate can be any possible correlation function, and still we are sure that the prior probability of any neighborhood of this true correlation function is always the probability of this of any open neighborhood of the true correlation function is always positive. So basically, the prior covers every possible correlation function. So we are not making any parametric restriction or limitation about the possible correlation function. So we can say that the proposed model falls within the framework of Bayesian non-parametric approaches. So as we said, we have assigned to B a prior probability. So we assume that we have also assigned a prior distribution so to B and also to sigma square. Conditioning on B and sigma square, the process Z is Gaussian with a given convolution covariance function, which is obtained multiplying our random correlation function by sigma square. And in this way, we have a joint distribution of B and Z. The marginal distribution of Z is a conditional probability distribution of Z. So what happens is that we observe the value of the process at n points x sub 1, s sub n. So we have an observation vector. The posterior distribution of our Schoenberg coefficients. So this is posterior distribution of B which is a condition distribution, is going to be the condition distribution of B given that Z of x sub 1, Z of x sub n is equal to the observed vector small z. So what can we say about the posterior? We can prove using, actually this result is obtained using a general version of the Bayes theorem, basically, which can be found, for instance, in Shervis' book, Theory of Statistics. So we can verify that the posterior of the Schoenberg coefficient is absolutely continuous with respect to the prior. So exist is unique, is absolutely continuous with respect to the prior, and the density, as usually happens, is proportional, the density of the posterior with respect to the prior is proportional to the likelihood, which is, we denote here by F, so is the n-dimensional centered multivariate Gaussian density evaluated as Z, with a given covariance matrix, which of course depends on the eigenvalue polynomials. And we have a normalized constant, which is we denote here by M of Z, which of course makes things a bit difficult on the computational side, because you don't have a close expression for this normalizing constant. It's an expectation of F, Z, and capital B, so B is the random sequence of the Schoenberg coefficients. So this is our posterior. We have a result about the well-posedness of the posterior. So basically, if the posterior varies smoothly as a function of the data Z, then it is robust to changes in the observed data. Small changes in the data lead to small changes in the posterior distribution. If this holds, we say the estimation task is well posed. So we can consider the Hellingen distance, and we can verify that the posterior is Lipschitz continuous with respect to the Hellingen distance in the data Z. So we have this result, which, as I said, is about ensure that the posterior varies smoothly as a function of the data. And about this topic, I want to mention the fact that we can consider other scenarios. So we are working about also other application about constructing based on parametric model in other scenarios. So in particular, there is a work about longitudinal integrated covariance functions, which is the submitted paper and is a joint work with Grazia Crinsus, Xavier Emery, Bernardo Nipote, and Emilio Porco. Then another work is about multivariate isotropic random field. There is a submitted work with Alfredo, Grazia Crinsus, Emilio Porco, and Philip White. Then other scenarios which we want to consider are space-time covariance functions, axis symmetric covariance function, and non-Gaussian random processes. So this is about what we are developing, or we aim at developing in the future. So finally, I don't know how much time I still have. I want to say something, not too much, about the issue of strict positive definiteness. As I said before, we have this inequality here. If this inequality is strict for every n over x sub 1, x sub n of points on the d-dimensional sphere, and every vector c sub 1, c sub n, which is not the known vector, then C is strictly positive definite. In geostatistics, one considers process Z at n distinct points, x sub 1, x sub n, And for the inference, we need the inverse of the covariance matrix of Z of X sub 1, Z of X sub n. So the issue is of statistical interest. In the isotropic case, it is known how to ensure that a positive infinite function is treated positive as well. In particular, we have one of the very first results about strict positive definite of spheres about the isotropic case is a paper by Xu and Cheney, published in 1992, and basically they prove that you ensure the strict positive definiteness is guaranteed if the Schomburg coefficients are all strictly positive. Then later, this result has been improved by Menegatto, and in his works, which he has written with Chen and San and Oliveira and Paron, and basically they find a condition which is not just sufficient but also necessary. And there are two different, the conditions are different if you consider the equal greater or equal than 2 or d equal to 1. And okay, I don't, basically if d is greater than or equal to 2, the condition that the coefficients are strictly positive for infinitely many even and infinitely many odd integers n. Instead, for the case d equal to 1, there is a completely different condition. So C is strictly positive if and only if given it two integers j and n, where j is between 0 and n, there exists an integer k such that b sub j plus k times n1 is positive. So about axial symmetry, as I said before, axial symmetry means that the covariance function depends on the longitudes, only through the difference between the longitudes. We have this representation provided by Jones, and the paper which I've written with Anna Peron and Emilio Porcu, published this year in Stochastic Environmental Research and Risk Assessment, we have generalized Xu and Cheney's result to the axial symmetry case. So basically, the condition is that a sufficient condition for strict positive definiteness in the axial symmetry case, in that you need this function C sub n to be strictly positive definite. So for capital C to be positive definite, you need C sub n to be positive definite. If they are also strictly positive definite, then capital C is strictly positive definite as well. So this is our result. It's a long proof. It's a long technical proof, which has turned out to be longer than I thought in the beginning, but we managed to prove this result. So it would be nice in the future to be able to find a condition which is sufficient and necessary. So this has not been done yet. So something that is still an open problem. Another thing would be to define axial symmetry on d-dimension spheres and try to understand the relationship between different spheres in different dimensions. And I'm finished. These are the references. Thank you.
Thanks, Pier Giovanni. Interesting talk. Is there any question? Please just speak out loud. Francisco Cuevas. Adelante, por favor.
Hello.
Hello.
Hello. Hey, hi. How's it going?
Well.
Hey, I have a question about your talk. So if you can move to the posterior result that you have.
Okay.
Yeah.
Wait a second. No, sorry.
Nah, no
The
worries.
posterior. This.
Yes, that one, yeah. So is that you say that the normalizing constant is a problem for a computational point of view, and of course I agree because compute data thing it's very expensive, but for simulating from the posterior there is some metropolis casting algorithm or something like that.
Well, to be honest, my contribution was about the theory, so
Okay.
I say that for now you can deal with it only if you have not too many data, of course. So, and I really would like to be able to create a model where the computational issues are more manageable. But
Yeah.
I mean, for now, yes, you can make it work for if you don't have too many data. But I cannot give you the details about how they managed to, my co-authors managed to.
Okay, but okay, I get it. No worries. Yeah, yeah, that's all. Thank you.
Okay.
Any more question?
I have a question.
Ronnie?
I'm actually wondering if this is kind of applications, but it is difficult to find a prior for an infinite number of parameters. But in a practical situation, can you say how to choose the prior for a particular problem?
Well, I would say that in general, it's not that difficult to choose a prior. You can choose a prior in different ways. Of course, it's better if the way you choose a prior doesn't affect too much your results, I would say. And I think we did empirically verify that. You can also, in the prior, you have hyperparameters, and you usually, this is what happens typically when you propose a Bayesian model. You want to make sure that the hyperparameters don't affect too much the results. We have used GM distribution. I think that we put alpha equal to 0. If I so I think that ideally, as I said, it would be nice to find a prior which let you know exactly what the integrating, the normalizing constant is. But so far I don't have an answer about that. So I don't think there is a general, there is not an answer that a prior is better than another one, apart from the computational aspects, and that you don't want the prior to be to have a you don't want that changing the prior you get the results which are too different.
Okay, thank you.
Yeah.
Any more questions? I have a question in the slide 29. in the theorem.
Mhm.
Is this construction also valid in psi infinity? Because this is for a fixed dimension D, right? Because you have the Eigenvalue polynomials.
Yes, actually, yes. I say, yeah. I definitely. It's you have a similar analogous result. You get the same in psi infinity. It's not going from psi sub d to psi infinity. You achieve the full support again. Yeah, using the same prior. Yeah.
Thanks.
Yes.
Any more questions? Well, I think there are no more questions. So thank you again, Pier Giovanni. Thank you again to the participants.
Okay.
And goodbye.
Okay, goodbye.
Bye.
Bye.
Thank you. Bye-bye.
Thank
Bye.
you. Bye.
Thank you. Bye. Bye.
Bye. Thank you.
Bye.